how many different ways can we scramble a Rubik's Cube? How can we even figure that out? Well, to start, we should first start by thinking about the corners and the edge pieces, because the thing that makes a scramble different from another one is the position of the corner pieces and the edge pieces. So to start, we know that there are 8 corner pieces. So 8 corner pieces, and there are 12 edge pieces. So we know the number of corner pieces and edge pieces that we have. But how can we figure out the number of ways to rearrange them? Because that's kind of what's happening when we're scrambling the Rubik's Cube. Well, first, we're thinking about permutations. The number of different ways or the number of permutations that exist for the corner pieces, and the number of permutations that exist for the edge pieces. Well, first, what would the number of permutations be for the corner pieces? Now, the number of permutations that exist for the corner pieces would just be 8 factorial. And the number of permutations that exist for the 12 edge pieces, well, would be 12 factorial. So this would be the number of permutations for the corner pieces and the number of permutations for the edge pieces. Now, when I'm saying permutation, I'm talking about the position of the corner piece. So we have this Rubik's Cube right here. And when I'm talking about position, I'm talking about, oh, this is a position of the edge piece. Or this is a position of the corner. This is a position of another corner. This is a position of another corner. And this is a position of another corner, right? Just where, it's basically where it's located. All right, the different permutations, the different positions. Right, position as in where is it located. So these represent all the different permutations for the corner pieces and the permutations for the edge pieces. So I want these permutations to exist at the same time because remember, for these corner pieces being located at different positions, so are the edge pieces. So they exist at the same time. If I want these permutations to exist at the same time, I just have to multiply them together. So I'm multiplying them together to show that we're finding when they exist at the same time. So we have all these different permutations of the corner pieces and the edge pieces. Are we done? Or did we account for everything? The truth is, we didn't actually account for everything yet, because there's another part of the Rubik's Cube that we haven't thought about yet. So, for example, let's just say we're starting off with a solved Rubik's Cube, and all of the corners are in these specific positions. So this is the specific permutation that we have. However, what happens when I do this? I didn't change the position of this corner piece. So they still have the same permutation. It's still a specific permutation of the corner pieces. But the thing that changed about it was the direction at which the corner piece was facing. And so that is what we also have to think about. We have to account for the direction that each of these different corner pieces and edge pieces face. So let's start with the corner pieces. So let's say we have what we had right here, right? We're just focusing on this corner piece. So this is one direction that the corner piece could face, right? The yellow could be facing this way. Or if it looks like that, the yellow could be facing that way. Or we could have the yellow facing this way. And then we're back to what we had before. And so as you can see, there's 3 different possible directions that the corner pieces could face. So if we were to just combine the different directions for one corner piece in what we have here, we would just be multiplying by 3, right? Because we're only in that case we would only be focused on one corner piece. But really, we're trying to account for all corner pieces and the directions, right? So all corner pieces and the directions. However, we actually are going to account for the directions that each of these corner pieces face, all of them except one. So we're going to account for all 8 corner pieces and their different directions except one of them. Why would we not account for one of these directions? Now this is one of the confusing parts of it. However, the reason why we aren't accounting for just one of those corner pieces is simply because we need a reference direction that one of the corner pieces face, so we know what to label the directions of the other corner pieces. And so as a result, I'm just going to multiply by 1 to show that's what we're talking about for the other corner piece and its direction. So now we're able to understand the different directions that exist for the other corner pieces. And this works the same way for the edge pieces. So for the edge pieces, let's say we're focusing on this edge piece, this yellow-red edge piece. Now, either we could have this edge piece looking like this with the yellow and red, or we could flip this edge piece around so that instead of it going yellow-red, it goes red-yellow. And so there's 2 different possible directions for an edge piece. So if I were to only focus on the different combinations that exist for this edge piece and combining it with what we have here, we would just be multiplying by 2. But we have to account for the directions of all of the edge pieces. So we're going to account for all of those 12 edge pieces except one of them, right? Remember, the thing that we're doing with that other edge piece is we're just going to multiply by 1. Now, of course, multiplying by 1, it's not going to change anything. But what I'm trying to show here is we already have a specific direction that we're going to label that edge piece. Because if we're able to label or understand the direction of one of those edge pieces, we can do the same for all the other ones. And so we're able to describe the different directions that exist for the edge pieces and the corner pieces. And so now we're able to account for that. So, is this the end? Would this give us the number of different scrambled ways to scramble the Rubik's Cube? Would this be it? The truth is, how do we even know that the cases that we've accounted for up here are even solvable? How do we know we can even solve all of these cases? So, first of all, let's just say we have a case that, well, let's just say we have this case again. And this case right here, where exactly one of the corner pieces is twisted, is a part of one of the things that we've written up here. Because we know that in this case, we know that each of the corner pieces have specific positions. Each of the edge pieces have specific positions. And all of the corner pieces, they're facing in a specific direction in which we're given the direction of one of those corner pieces. So we're able to understand the direction of the other corner pieces. And we know that each of the edge pieces are also facing in specific directions relative to one of those edge pieces. So, this case where exactly one of the corner pieces is twisted does belong to one of these cases that we've basically written up here. But the thing is, we know that this case where exactly one of the corner pieces is twisted isn't solvable. This case where exactly one of the corner pieces is twisted cannot be solved. You cannot, or in other words, you cannot physically turn the cube in such a way where this corner piece becomes solved. You cannot just turn the cube and solve the case. It's impossible to solve the cube when exactly one of the corner pieces is twisted. And so that's the other factor that we have to account for here. It's determining whether, or basically removing all of the unsolvable cases from this value. We need to only account for solvable cases. Because remember, we're talking about cases in which, well, cases in which we are scrambling the cube too. So if we're talking about cases in which we can scramble to, then we should be able to solve those cases. So we have to only account for cases that we can solve for. So what do we do to do that? Now, the way that I'm going to approach this is I'm going to introduce the idea of something known as a swap. Now, I'm going to start by first creating or making this case. So this is a case, this is actually one of the cases that exists in blindfolded Rubik's Cube solving, in which the goal is to simply swap out these two edge pieces. Now, the truth is, you can never make exactly one swap. And a swap is basically just switching the positions of two pieces, right? It could be two edge pieces or it could be two corner pieces. In this case, we have the swap of two edge pieces. However, we cannot just do the swap of two edge pieces. There has to be something else that is swapped. Right? You cannot swap exactly one thing. Right? And so in this case, there's actually a swap of the edge pieces and there's a swap of the corner pieces. And so I'm going to draw this off to the side actually. So I'm going to draw the top layer. I'm going to draw the top layer. In this case, it's the yellow. And so what this looks like, it looks something like this. So I'm drawing the yellow face and I'm just going to make dashed lines to represent the different pieces. Actually, I'm going to do this. I'm just going to do this. Make it easier to see. So we have our 3x3, and this is the yellow face. And basically, I'm going to show the swaps using double arrows. So there's a swap between these two edge pieces and a swap between these corner pieces. So swapping these edge pieces and swapping these corner pieces. So yeah, swapping edge pieces and swapping corner pieces. That's basically what's going on with this case. And the way that we would solve this case is, well, so you can see we would be switching these pieces out and switching these pieces out. There is a way to physically move the cube by turning it in order to solve that case. And the reason why we're able to solve a case like that is because in that case, there is an even number of swaps. In this case, there are two swaps that were made. So a swap right here and a swap right here, represented by those arrows. Now, this is a really important idea of the basics of a Rubik's Cube, actually. It's the idea that when we turn a Rubik's Cube, this is what happens. Every solvable case in a Rubik's Cube has an even number of swaps to it. So when we were solving this case, the reason why we were able to solve this case is because there was an even number of swaps. If we were only trying to swap the edge pieces and not the corner pieces, so just the edge pieces, that would be impossible to do just by simply turning the cube. Right? It's impossible to do that. So that would actually, in fact, when I say there's an even number of swaps, so even number of swaps, that's actually known as an even parity. And if it's an odd number of swaps, that would be an odd parity. But I'm not going to go into that. Basically, it's an even number of swaps that you need in order to solve the cube. So either you can have an even number of swaps or you can have an odd number of swaps. If it's an odd number of swaps, so if we were actually, let's say I was also switching these pieces, and this is all I'm doing. I'm only focused on the top layer. I'm not worried about, right, I'm just gonna go back to this case. I'm only, right now, I'm just keeping this really simple. Right? I'm not going too in depth with this idea of even number of swaps, odd number of swaps. But this is a really basic idea of the Rubik's Cube. Every solvable case is represented by an even number of swaps. And right now, I'm just focused on this top layer when swapping out these pieces. I'm only focused on the top layer. I'm not focused on these bottom layers, right? But they would work the same way, right? There always has to be an even number of swaps. So this is what we have. If we have an odd number of swaps, this would be unsolvable. This is impossible on a 3x3 cube. And so on larger cubes, you would actually get something known as a parity. So how do we account for this in what we have right here? Well, half of all the cases that we are going to get here involve an even number of swaps, and the other half involve an odd number of swaps. So in this case, I'm just going to delete this arrow because that's not what I was showing. Really, the case that we were looking at was an even number of swaps, of course, all right? And this is actually known as Perm, right? It's one of the last steps in solving the Rubik's Cube that you can know. And so this is basically what we have. We are dividing by 2 because half of all the cases in here involve an even number of swaps, and the other half involve an odd number of swaps. And so half of the cases are solvable, half of them are not solvable. And so this value that we see right here would be the number of cases that are solvable when scrambling the Rubik's Cube. And the case that we have right here is, well, this case is just one of these numbers, right? This is in fact a really large number. This number is about 4.3252 times 10 to the 19. So if I were to move this decimal place 19 digits to the right, that's a number about 43 quintillion 252 quadrillion. And to put this in perspective, one quintillion is 1,000 quadrillion, and 1 quadrillion is 1,000 trillions. This is the number of cases that exist that are solvable for a Rubik's Cube, right? It's this number of cases. Now, here's the thing. This is the last thing I'm going to go over. Why is that number so big? I mean, we're only concerned with 20 pieces on the Rubik's Cube. How can we get a number like this that's so big? Well, actually, that's a good question. But really, no, but seriously. The reason why this number is so big is actually has to do with the types of values that we're using with these numbers. In fact, these are factorials, and they are some of the fastest growing functions, right? Factorial functions. They are some of the fastest growing functions out there. So 12 factorial is like really large. In fact, when you say something's exponentially growing, that's nothing compared to growing at a factorial rate. Factorials grow faster than exponentials. And right here, we're multiplying factorials by exponentials, and that's what makes this value really large. And so, well, this is it. The number of possible cases that you can get from scrambling a Rubik's Cube.